Light now, across the Netherlands, thousands of machines are quietly working to stop water from reclaiming the land. Not one giant structure, not a single wall. Pumps, gates, locks, canals, and sensors are all working at once, and the lowest parts of the country cannot simply drain by gravity. If that network stopped for long enough, water would begin collecting in the deepest polders within days. One of Europe's busiest airports sits about 4.5 meters below sea level. Millions of people live in areas that depend on this system, yet most of them can travel to work without ever seeing the machinery that keeps the ground beneath them usable. People call it the machine that keeps the Netherlands from drowning, except there is no single machine. 3 jobs, not one machine. The real machine is an entire country-sized network built around 3 jobs. Job 1, keep dangerous water out. Job 2, move water across the country before it pools where it should not. Job 3, lift water out of land that sits too low to drain on its own. Dikes and dunes handle much of the first job. Canals and locks guide water through the second. Pumping stations do the third. Storm surge barriers wait at vulnerable openings along the coast, while sensors, forecasts, and regional water authorities coordinate the system above them. Think of a human body with a heart, but no arteries, lungs, or nerves. The heart could still beat, but the body would fail because nothing around it could move, balance, or respond. The Netherlands works the same way. No single structure keeps it dry. But that creates an obvious question. If water is the threat, why not just build the walls higher and be done with it? Why not just build the walls higher? Because the water does not come from one direction. The North Sea pushes inward. The Rhine, Meuse, and Scheldt carry water toward the coast. Rain falls inside the defenses. Groundwater seeps into low-lying polders. A taller coastal wall may reduce one danger, but it cannot empty a field that lies below the canal beside it. And rivers create another problem. Squeezing more water between ever-higher dikes can raise water levels and leave less room when extreme flows arrive. Higher defenses remain important, but height alone cannot manage the whole system. The Dutch solution is not one perfect wall. It is a network that keeps water out, moves it sideways, and lifts it upward, often at the same time. How the machine actually works. Imagine a heavy storm crossing the Netherlands. Rain falls over cities and farmland. Rivers carry water west toward the sea. Strong winds push North Sea water toward the coast. The country is being pressured from outside and filled from inside. First, dikes, dunes, and coastal barriers prevent the most dangerous seawater and river levels from spreading directly across the land. Behind them, canals act like controlled plumbing. They collect rainwater, river overflow, and groundwater, then guide it toward places where the level can be managed. Much of the country is divided into polders, low areas enclosed by dikes. Some sit below the rivers and canals around them, so gravity cannot carry the water away. It has to be lifted. That is the job of pumping stations. They move water from a low polder into a higher canal. From there, another route, and sometimes another pump, carries it toward a river or the sea. It is like moving water up a staircase, one level at a time until it can finally leave the country. Locks solve a different problem. Where 2 waterways sit at different heights, a lock isolates a chamber, changes its water level, and lets boats pass without allowing the higher side to flood the lower one. At the coast, storm surge barriers normally remain open so rivers can drain and ships can pass. They close only when forecasts predict dangerous water levels. Every part has a different job. The remarkable part is that they have to perform those jobs as one system. The system's brain. That coordination begins long before anyone sees a flood. Water level sensors measure rivers, canals, and the coast. Forecasting systems combine those readings with tides, wind, rainfall, and river discharge. Water managers use the result to decide when to lower canal levels, increase pumping, close a barrier, or prepare emergency measures. The system is not waiting for water to arrive, it is trying to create room before the water gets there. And that matters because once water begins moving through a breach, the time for prediction is over. What happens if the system stops? A failure does not make the entire Netherlands disappear beneath the sea overnight. The first problem would be accumulation. Rain and groundwater would continue entering the lowest polders. But without pumping, that water could not climb into the higher drainage network. Fields and roads would become waterlogged. Local water levels would rise. Infrastructure in the deepest areas would face growing pressure. The network contains backups and alternative routes, but not every failure is equal. A pump can sometimes be replaced or bypassed. Water may be redirected through another canal. A damaged dike is different. Once a breach allows high water into land below it, gravity starts working for the flood instead of against it. That is the weak link. Behind the final line of defense, there may be nowhere lower for the water to go. The Dutch learned that lesson in the worst possible way. The night of 1953. On the night of February 1st, 1953, a violent North Sea storm combined with a high spring tide. Water drove against the southwest coast harder than many of the existing dikes could withstand. Dozens of breaches opened while people were asleep. Seawater rushed into towns and farmland. By the time the scale of the disaster became clear, 1,836 people in the Netherlands had been killed and tens of thousands had been forced from their homes. The flood proved that the existing defenses no longer offered the protection the country needed. The response became the Delta Works, a vast program of dams, dikes, sluices, and movable storm surge barriers designed to shorten the exposed coastline and reduce the chance of another catastrophe. But one opening could not simply be sealed, the system's boldest answer. The Maeslant Barrier near Rotterdam, the Nieuwe Waterweg, carries ships between the North Sea and one of Europe's largest ports. A permanent dam would protect the land, but it would also block the shipping route. So engineers built two enormous floating doors that normally rest in docks on opposite banks. Each door is 210 meters wide, longer than 2 football fields, and connected to a steel truss that swings around a giant ball-and-socket joint. No flood barrier in the world has larger moving parts. When forecasts predict an extreme surge, the closure system starts automatically while operators monitor the process and can intervene if necessary. The doors swing into the channel and meet in the middle. They then fill with water and sink onto the riverbed, sealing the waterway. After the surge passes, the doors are emptied, rise again, and return to their docks. The port reopens, and the barrier almost disappears from everyday life. That is what makes it so extraordinary. One of the largest moving structures on Earth spends most of its existence doing nothing because the entire system is designed to act before the worst moment arrives. Why the Dutch change strategy? For centuries, the instinct was simple. When water rises, build higher. The Netherlands still strengthens dikes, but engineers also learned that walls cannot be the only answer. Sea levels are rising, heavy rainfall is becoming a greater challenge, and rivers sometimes need more space rather than tighter boundaries. Under room for the river, dikes were moved inland in selected locations so high river water could spread into controlled floodplains instead of being forced toward cities. In Rotterdam, some public squares temporarily store stormwater and return to normal use after it drains away. Along the coast, the sand motor uses a large artificial deposit of sand and natural currents to distribute that material along the shoreline over time. The strategy is no longer simply to resist water everywhere. It is to block it where necessary, move it where possible, and give it controlled space where that is safer. The Netherlands has not defeated the sea. It has built a system that never assumes the work is finished. Every pump, gate, canal, forecast, and inspection protects one small part of the balance. Together, they keep farms productive, airports operating, and cities standing on land that water once occupied. That system is now studied by coastal regions around the world. But its most important lesson is not the size of a barrier or the power of a pump. It is this: some problems are not solved once. They are kept from winning one ordinary day at a time.